Hello students, in this video we'll discuss how to find slopes of parametric curves and do an example with the involution of a circle. If we're given a parametric curve, x equals f of t and y equals g of t for t between a and b, I'd like to find the formula for dy dx. Find dy dx. Okay, so to do this, what do we need to do? Well, we need to say, is there a relationship between y and x? So if one of these functions f or g are invertible, I can write y as a function of x. If we write y is a function f capital of x, then I can use the chain rule. Then, by the chain rule, I can say that dy dt is the t derivative of this thing over here. But of course, x is a function of t. So what will this be? This is going to be f prime of x, which is the df dx, times dx dt. And so this thing over here is exactly just dy dx. So we've just shown that dy dx is what? Dy dt over dx dt is dy dx. And so that's the important formula. Remember that if you want to do the ratio, if you want to find dy dx, you compute the ratio of dy dt to dy dx. So let's see an example of how we would do this. So what I'm going to do is I'm going to derive a formula for a curve. And so this is a fun example. And so let's consider this procedure over here. Okay, so I'm going to draw just the unit circle. And I'm going to wrap a chord around this unit circle. Okay, so there's a piece of string that's wrapped around it. And what I'm going to do is I'm going to hold this string as tight as I can, and I'm going to pull the string and I'm going to loop it around the circle. So I'm going to pull the taut and move it around. So I'm going to unwrap it basically. So let's think about what's going to happen over there. So what will happen is that trajectory will do something like this. It'll unwind like this. And this procedure is called finding the involution of a circle. And so here's the idea. And so what do I have to do? How can I find a generic point on this curve over here? So what I'm going to do is I'm going to draw an angle theta over here, and then draw a perpendicular to that curve. So that's going to be a perpendicular line segment, and that's going to be a point on my curve xy, which I'd like to find over here. I'd like to find that point xy. Now the key feature of this is, since I'm holding it taut, the arc length that I've cut out over here has to be the exact same as the length of that perpendicular over here. So the key feature of this procedure, and this is what defines the involution, is that this length over here, that perpendicular length, is exactly equal to theta as well. Okay, that's what it means to hold taut in this context. So that's an angle of theta, and so of course we can extend this out to a triangle, and then drop that triangle down over here, and drop it over here. So I'm going to form two right angles. Now, of course, if this angle is theta, then this angle over here is also theta. And if we think about this for a second, this is also going to be a right angle over here. So these two triangles are similar, which means that this angle over here is going to have to be theta as well. So that angle over there is going to be theta. We'll write that in a second. So now that's the problem. So we'd like to find out what the equation of that point is. So what's the x coordinates? So whatever this length is over here, okay, so this length is a unit circle, so that's a length of what? This point over here. I can also draw the sine and cosine from that angle over there. What will it be? This is going to be what? That's going to be cosine of theta down here. And that length over here is going to be sine theta up here. Okay? Good. So what? So now, to find the x coordinate, I'm going to have the cosine of theta plus this extra length over here. That extra length will give me what the x coordinate of this thing is going to be. And let's think about what that will be. Well, what's going to happen is that, as I mentioned too, we're going to say that these two triangles are similar to each other. So what will happen is that this angle over here is going to be theta. And then this side length over here is going to be what? That's going to be the cosine theta, and this is going to be the theta sine theta, because that's the hypotenuse. And then this length over here is going to be what? Is going to be theta cosine theta. Okay? So now I can put all of this together and figure out what the parameterization of this involution is. So the involution has parameterization What will the x be? Okay, as we see the x is going to be what? It's going to be cosine theta plus theta sine theta. Cosine theta plus theta sine theta. And what will the y be on this involution curve? Well, the y is going to be what? The y is going to be, the y height over here for that point is going to be sine of theta minus theta cosine theta. So it's this big height over here minus that little length of a circle. So it's going to be what? It's going to be sine of theta minus what? Minus theta cosine theta. Okay? And so now I'd like to ask the question for the involution of the circle. So the question is, what's the rate of change of the involution of the circle, dy dx? So find, our example will be defined, find dy dx for the involution. Okay, so let's do it. So what will dy dx be? So dy dx is going to be dy d theta over dx d theta. Okay, so what is dy d theta? Dy d theta is going to be cosine of theta minus, and I got to do the product rule, so it's the first function times the derivative of the second. So that's going to be a what? That's going to be a derivative of cosine is going to be a negative sine, so it's going to be theta times negative sine theta. And then the second function times the derivative of the first, that's plus cosine theta. Okay. And then the bottom is going to be what? I got to do dx d theta, which is going to be negative sine theta plus sine theta, and then plus theta cosine theta. Okay? So look what happens over here. In the numerator, the cosine is going to cancel, and the denominator, the sine is going to cancel. So what are we left with? We're left with in the numerator, theta sine theta over what? Theta cosine theta. The thetas cancel out. And so that says for the involution of the circle, my dy dx is really just the tangent of theta. So for the involution of the circle, the slope is the tangent of theta, where theta is the angle at which the rope has been, or the rope or the string has been pulled out along the x-axis in a taut fashion. Thank you very much.